Doing this Feynman Hibbs integral will make you a quantum theory expert. So this integral was found in one of the books of Feynman as well as in another quantum theory books of Hibbs. So this is known as Feynman Hibbs integral, and this has a very elegant answer. Not so elegant, but yeah, it's a nice answer. And yeah, so in this video we'll see how to solve this one. This is integral from 0 to t e to the power minus a by t minus tau minus b by tau t minus tau to the power 1 by 2 tau to the power 3 by 2 d tau. Let's start this tau as x because t doesn't really look good. Integral from 0 to t e to the power minus a by t minus x minus b by x. So this minus is actually in the power, so let me write over here. Minus b by x divided by t minus x to the power 1 by 2 x to the power 3 by 2 dx. Okay. Now what I can do is to make sure that this goes from actually 0 to 1 so that it's easier to integrate. What I can do is, let me say that u is equals to x by t, because if I do that only, then this will be simpler. Yeah. So now if I do that, it will be integral from 0 to, this will be 1 e to the power minus a by t minus, this is ut, yes, minus in the power minus b by ut divided by, this is t minus ut to the power 1 by 2, and then again this is again ut to the power 3 by 2. Yes. Now since x is ut, since x is just ut, so that will be t times du. Okay, looks good. Yes. Now what I can do is, to make this simpler so that the t vanishes, let me say that a is alpha times t, b is beta times t. If I say that, I can substitute alpha and beta and the t cancels out. So you have integral from 0 to 1 e to the power minus 1 by e to the power minus alpha, e to the power minus alpha by 1 minus u, and then minus again this beta by u. Just and with okay. Good. And divided by, now this is 1 minus u to the power 1 by 2 u to the power 3 by 2, and t to the power 1 by 2 to the power 3 by 2 will be t square. Yes, it will be t square, and then over here t du. Yes. Now this t and the 1 of the t cancels out, so we have 1 by t outside. Now get 1 by t integral from 0 to 1 e to the power minus alpha by 1 minus u minus beta by u by 1 minus u to the power 1 by 2 u to the power 3 by 2 du. Okay, this is the integral. Now to solve this, let me make a change that instead of this like small power is in 1 minus u right now. Yes. So what I can try to do is, we can cancel this thing. We can cancel this thing out if we make a substitution that y is equals to 1 by u. If I make the substitution, we can cancel the second expression. So let me show you how. If y is 1 by u, then 1 by t integral from 0 to 1 e to the power minus alpha y by y minus 1 minus beta y. Yes. By, now this is y minus 1 to the power 1 by 2 times y to the power 1 by 2. Yes. Similarly, this goes up, y to the power 3 by 2. and then du will be minus 1 by y square du. Also, if I do 1 by u, the limits of integral will change, so this will now be the integral from infinity to 1. Yes. So since negative sign reverses this, actually this and these two will cancel out. Yes. Now the negative sign reverses the limits of integral, so we have 1 by t integral from 1 to infinity, and then e to the power minus alpha y by y minus 1 minus beta y by y minus 1 to the power 1 by 2 dy. Okay, now we can take that z is equals to y minus 1. So if we do this will be 1 by t integral from 0 to infinity, and e to the power minus alpha y is z plus 1 by z minus beta y is z plus 1 divided by this z to the power 1 by 2 dz. Yes. Okay. Now next is 1 by 2 integral from 0 to infinity. This is e to the power minus alpha by z, then e to the power minus beta z minus beta divided by z to the power 1 by 2 dz. Good. Now I can take it to the power minus alpha to the minus beta outside, and then I will get e to the power minus alpha minus beta by t integral from 0 to infinity e to the power minus alpha by z minus beta z by z to the power 1 by 2 dz. Again, let's make a use substitution. That u is z to the power 1 by 2, so that u square is z. So we get e to the power minus of alpha plus beta by t, and then integral from 0 to infinity of, now this is e to the power minus alpha by z is u square minus beta times z is u square divided by, now z to the power 1 by 2 is just u, yes, and dz is also 2u du. So now 2u the u cancels out, and then we have 2 times e to the power minus alpha plus beta by t, and the integral from 0 to infinity. This is the integral e to the power minus alpha by u square minus beta u square by du. This actually is also a kind of a standard integral, yes. So I actually know its solution, so I'll put it, but I'll also derive the solution afterwards. So for now, let us just put it e to the power minus of alpha plus beta by 2 by t. Now its solution will be 1 by 2 times root pi by this beta, yes, the thing that is there with the u square, and e to the power minus 2 root alpha plus root beta. So this is the answer. This answer can be further simplified by using the fact that, okay, now for now just know that over here these two coefficients will be there, and in the denominator coefficient of u square will be here, and 1 by 2 as it is. 1 by 2 as it is, root under pi by this coefficient, and e to the power minus 2 times root alpha plus root beta. Yes. Now up to this, now let us simplify it using the fact that a is alpha t. If we use this fact, now I can say that t is a by alpha. Similarly, t is b by beta. Yes. If we use this fact, now we get 2 times e to the power minus of alpha is a by t plus beta is b by t into 1 by 2 into root under pi times beta is b by t. Yes, and then e to the power minus 2 of root under alpha, root under a by t plus root under b by t. Yeah, looks good. Now after this, we have 2 times e to the power minus a plus b by t, and then this 2 and 2 cancel out, divided by t. Let me cancel this 2, divided by t. After that, this is just root pi. Since there is root t and there is t, so I can also cancel this root t, so that I can make it as, so we can cancel this t with the root t and then get pi by b times t. Yes, over here it is e to the power minus 2 root a. Okay, wait a second, this is not actually the sum, this is product. My bad. This is actually root ab, and I will derive this solution in some time. Wait for that, but for now I'm just trying to get the main solution. So this is actually product, not the sum. I'm sorry for that. Okay, this is actually the product. So we have 2 root ab by t. Okay, so now after this I can add these two, so that we get root under pi by bt, e to the power minus 1 by t. This is root a square plus now this is 2 root ab plus next is root b square. Yes, so we have root under pi by bt. Yes, and then e to the power minus 1 by t. This is root a plus root b square. Yes, this is the solution. So yeah, let's check the answer if it's correct or not. Root pi by b times t. Yes, e to the power minus 1 by t, root a plus root b whole square. Yes, so yeah, this solution works. Now in the middle, like I had just skipped some steps and gave you the perfect result, but now it's time to derive that result. Yes, now let us do that. Over here, let us try to answer this question. Let me write it in a different way. What I will try to do is integral from 0 to b into infinity e to the power minus p x square minus q by x square dx. I will try to prove this as 1 by 2 root under pi by p and then e to the power minus 2 root pq. I will try to prove this result. This is same. Yes, coefficient of x square is p, here was beta, so that's why we had beta, and root 2 root alpha beta, same thing. So let us try to prove this. Now before I prove this, let me call this I. Yes, and what I'll try to do is I will try to simplify this number of constants. There are 2 constants right now. I can actually decrease it. If I make a substitution that not the black, I want to use red. Okay, if I make a substitution that u is equals to root p times x, and this variable will decrease. No, it will not decrease, but we will definitely. Okay, let's see how. So if we make a substitution, this substitution, now I will be integral of, again, 0 to infinity itself, e to the power, this will be minus u square minus q by x square will now be u square by p. Yes, and then now dx will be du by root p. Yes, so now I will be equals to 1 by root p integral from 0 to infinity e to the power minus u square minus pq by u square du. Yes, again what I will do is I will let k square is equals to pq. That means let k be the geometric mean of pq. I'm just doing this so that this variable reduces. Yeah. So then we will have I is equals to 1 by root p, And the reason I'm doing k square, there's a reason for that. I could have just done k, yeah, but why I'm doing k, so there's a reason for this. This so that later on, while using Feynman's technique, the integral will simplify. Yeah, you will see how. And now again, this is just a supposition, so no limits of the integral or nothing, just constants being supposed. Yeah, integral from 0 to infinity minus u square minus k square by u square du. And now it looks good. I actually want to solve this integral. This is a simplified version of this integral, which I will solve. Now in this integral, let me again take this as I of k. Let me take it z of k, because I of k is already here. Yes. Now let me say that the j of k is this integral from 0 to infinity of this e to the power of over the e to the power minus u square minus k square by u square du. Yes. Now if I say that, okay, so now if I differentiate this with respect to k, yes, if I differentiate this with respect to k, what I will get is integral from 0 to infinity. Yes. Now over here, powers of u will remain as it is first, yeah, e to the power minus u square by k square by u square, and then we will differentiate this power. This one goes to 0, and this one will become minus 2k by u square. Yes. And now and then du as it is. Now the benefit of doing this is, now if I let x as k by u, x as k by u, sorry, k, yes, x as k by u. Now what I will get is, this thing cancels out, and these two will interchange. Okay, also z s of k will be integral from, now this is from infinity to 0. Yes, e to the power, now this will be minus k square by x square. Yes, and this will be minus x square. Over here we will have minus 2k by u square, and since x is k by u, yeah, okay, so do 2k by u square, and also we know that dx will also be minus k by u square du. Yes, so since this is minus k by u square du, I can actually erase this k by u square. Also I can erase this minus sign. Actually I can also erase all these minus k by u square du, and then write it as dx. Yes. Now over here you should notice something, that actually first of all I can also reverse this integral to take a negative sign. Yes. And next thing you need to notice is, this is actually the same, e to the power minus x square minus k square by x square. The integral is actually the same, just that there is a minus 2 sign and then dx. Yes, so this is actually the integral that we started with earlier. So I can say that this is z s of k is actually just minus 2 times j of k. You see that? Yes, and this is an interesting observation that will help us to solve this integral, because now I can say that this is just dj by dk will be equals to minus 2j. Yes, and then after that we will have dj by j is equals to minus 2 dk, and after that this will be ln of j will be equals to minus 2 times k plus some constant, so j will be equals to e to the power minus 2k times e to the power c. Now to find k, okay, now to find k, the value of k in this, or I mean to find the value of e to the power c, what you can do is, if you put k equals to 0, we get j of 0 as the popular Gaussian integral. Yes, e to the power minus u square du. We can actually solve this easily if we just convert this to a double integral and then take the square root, and the double integral comes out to be pi by 4, and so the square root will be root pi by 2. There you can find lots of sources on the YouTube how to solve the Gaussian integral. And yes, this is root pi by 2. So if you put that values over here, now j of 0 is just root pi by 2. And if I put k equals to 0, this will be 1 dot e to the power c. So you can see that e to the power c equal to root pi by 2. So therefore j will be e to the power c root pi by 2 times e to the power minus 2k. Yes. So this is actually the solution of that integral, root pi by 2 times e to the power minus 2k. This is the solution of this integral. Yes. Now let us go over here. We know that solution is root pi by 2 times e to the power minus 2k. So I is equals to 1 by root p times root pi by 2 e to the power minus 2k. Good. Now we know that k is just root pq. Yes, so therefore we will have I is equals to 1 by 2 times root pi by p e to the power minus 2 root pq. This is the solution. Yes. This is the solution. Yeah, and I guess I had to prove this. Yes, I was planning to prove this. Yes. So the same thing that I was planning to prove, and I have proved this, so that's why now I can use this result and solve this integral. So now that we have finally solved this Feynman Hibbs integral, now are you in quantum theory expert? I'm not sure if you are, but yeah, solving this integral involved lots of ideas, and these ideas will definitely be of your good for in some time in your life. Hope it will be helpful. Thanks for watching. Now let me just retell the flow of the solution. First of all, we reduce the variables, and then after reducing variables, what did it do? I tried to remove the c to the power 3 by 2 over here from the denominator to simplify it, and then we reversed it. Yeah, just simplify this, and now after that I reduced this again to go from 0 to infinity, and then over here we made a plan to simplify this integral by using u equals to the power 1 by 2. After that, this was an standard integral, so we solved it. Now to solve this, we had to use Feynman's technique. And again, for Feynman's technique, first of all I reduced the variables into a single variable, and after that this involved Feynman's technique. Yeah, we are first letting it as k by u, and then this will reverse over here. Also we will have something that cancels on later on while making the substitution. Yes, and yeah, and that solved the problem. So thanks for watching. I hope you enjoyed. Look forward to seeing the upcoming videos too.